Knock on a heavy wooden desk or grip a piece of solid steel. Your senses tell you that matter is dense, continuous, and unyielding. But in the early 1900s, the actual physical arrangement of what you were touching remained one of the deepest mysteries in science. By 1911, scientists had already identified that atoms contained negatively charged electrons and positively charged protons. What they didn't have was a working map. They knew the ingredients of matter, but they had no data on how those pieces were distributed inside the atom itself. Enter Ernest Rutherford. He was a physicist determined to find the atom's internal structure and locate exactly where those positive and negative charges lived. The problem Rutherford faced was one of scale. Atoms are far too small to observe with visible light. He couldn't put an atom under a microscope, slice it open, and look inside to see how it worked. To map the invisible building blocks of matter, he had to abandon direct observation. His only option was to shoot particles into the dark, hit a target, and analyze the microscopic wreckage that came out the other side. This meant building a specialized physical testing environment, relying entirely on the tactile, mechanical engineering of early 20th century physics. The gun for this test was a radioactive source, polonium metal. Polonium acts as a natural emitter, and Rutherford used it to fire approximately 20,000 positively charged alpha particles, heavy, high-speed projectiles, in a single direction. Placed directly in the line of fire was the target, an impossibly thin sheet of gold foil. It measured just 0.00004 centimeters thick, meaning the alpha particles would have to pass through the gold atoms themselves. Looking at a blueprint, Rutherford used a fluorescent screen to detect radiation, producing a flash on impact. The expectation was simple. If an atom was uniform, heavy alpha particles should punch straight through the gold foil and hit the back screen without changing direction. The moment Rutherford powered on the emitter, theoretical physics was replaced by high-speed ballistics. This animated diagram maps the first batch of incoming data. Out of 20,000 fired particles, 19,990 passed completely straight through the gold foil. They didn't hit anything. To contextualize this, imagine firing marbles into a massive empty stadium. The marbles fly from one end to the other without grazing a physical object. Since almost every alpha particle passed straight through without hitting a barrier, Rutherford made his first major deduction. Most of the volume occupied by the atom is empty space. But the map highlights a second dataset. A few particles were deflected off course at small angles. Because similar positive charges repel each other, these projectiles were reacting to a positive force pushing them away inside the foil. This gave Rutherford his second deduction. The atom contains a localized positive portion in the center that pushes the passing alpha particles away. An atom being mostly empty space with a central positive portion was surprising enough, but the final trajectory recorded on the screen contradicted the existing models of atomic structure. Watch this specific path on the diagram. A tiny fraction of the alpha particles hit the foil and bounced directly backward, returning the way they came. Returning to our stadium analogy, this is like firing a marble that strikes a tiny concrete pillar in the center and ricochets straight back. To bounce a heavy alpha particle backward, it had to hit something exceptionally dense. Rutherford concluded that the atom's positive charge is concentrated in a microscopic center point, which he called the nucleus. This ricochet proved that the mass of an atom is not spread out. It is concentrated in a central point, so dense it can repel a high-speed projectile. Rutherford proposed a new architecture. The Planetary model places the nucleus of positive protons dead center. Electrons follow sweeping orbits around the nucleus, like planets circling the sun. The atom remains neutral. Negative electrons equal the positive protons. Applying this microscopic map to the everyday world means the heavy wooden desk or solid steel you touch is mostly a vacuum. Physical matter is 99% empty space. By tracking a few deflected particles in the dark, Rutherford proved that the mass and energy of our entire physical reality are concentrated in tiny, invisible centers of matter.